Hello, my name is Carlos Reda, and in this session, I'm hoping that you're actually liking the panels on the session that we're preparing for you so far. In this session, we're going to go ahead and explore a bit more about financial services industry grids and how basically we onboard those grids onto AWS. In particular, we're going to be joined by Daniel Kazarinow, which is the head of cloud SRE operations and grid at the Standard Chartered Bank, and we will see how our customers are adopting grids onto AWS. My name is Carlos Manzanero Rueda. I'm a specialist SA working and specializing on spot instances and high performance compute at AWS. In this session, we will have three parts, right? The first part, we're going to focus on the context of how financial services are using AWS services and onboarding their grids into AWS, checking the context and the added value that AWS brings together. The second part is going to touch point of the added value of the services that we bring together to move those workloads onto AWS. And finally, we're going to be hearing from Daniel, how was the journey of Standard Chartered on adopting those techniques and services. For financial services institutions, it's all about measuring and managing risk. My background is capital markets, where we use grid compute or high-performance loosely coupled compute to analyze using numerical methods like Monte Carlos, partial derivative equations, and so on. What is the present value of certain products? And with those values, we can basically make a hedging decision. So provide all the reports to the regulators and stakeholders to understand that we're doing good governance around the risk that we are creating. But it's also used in banking and payments industry, for example, for fraud detection, or in the case of insurance, for actuarial modeling, same stochastic calculations for a sample of the population to understand what are the risks that apply to that part of the population. And once that we understand the risk, then we can take steps. This is where the added value to the business of having those risk calculations done in a high-performance compute environment, large high-performance compute environment. We can proactively reduce the risk that we are exposed to, understand the sensitivities of our models and the sensitivities of our portfolios to decide basically how to best place our portfolios and manage our portfolios. Let's move to understand a bit where high-performance compute is used in the trade lifecycle. So this is a very simplification of the trade lifecycle in an investment bank. There's primarily two cases where high-performance compute is used. At the very beginning of the change, where the very execution is done. So we're talking over here about non-trading books or orders that need to be evaluated at a point in time during the online or intraday to understand, for example, what is the present value of a specific product, just to see if you are going to have buy that product or sell that product and so on. But also as part of the trade lifecycle itself, when the execution and the confirmation of the trade has been done during the overnight batch to do the trade management, the management of your portfolios and reporting that is required for regulators, and at the beginning of the day for the desks to understand what is the current position that they can work on. So there's an online and an overnight batch effectively that uses the grid. How these systems look like internally for the financial services industry. So this is, again, a simplification of one of those risk analytic platforms. You can see the orange arrows where the whole thing starts with the triggers and a pipeline that goes from generating a scenario, getting the scenario that you are trying to represent for your risk analysis, then fetching the data, the market data, the trade data, the reference data that is required to calculate and analyze that particular scenario with all the trading books, doing the pre-processing, and finally going into this calculation phase. This is where the high-performance compute, loosely coupled high-performance compute or grid computing is done. Primarily, the crown jewels of these institutions on the quantitative analytic libraries are the one that will compute those numerical methods that we just mentioned, these Monte Carlos, PDEs, partial derivative equations, and finite difference equations, and solvers that we use to price these models. And finally, we do the post-processing and store and aggregation. And some other triggers can basically start other processes for the calculation of other risk, other part of the risk in the pipeline. So that's where the high performance compute is engaged on those models. Traditionally, when we were working on premise, this was the utilization profile of this grid. So you see that around 6 p.m., 5 p.m., 6 p.m., markets will close, will trigger on the grid. 8 p.m., the bulk of the batch calculation for the overnight will start and will ramp up until it uses around 12 to 1 a.m. all the compute capacity that we had in our data centers on premise, right? And at 6 a.m., all those calculations need to be done, so in preparation for the next day, for the regulators and also for the trading desk to get those reports before the markets open. And during the day, you can see that not all the capacity was used, and therefore we got quite a lot of unused capacity over there during the intraday, but the capacity is still needed for this online that we were talking. When our customers move to AWS, what we see is that the profile changes. What we can see in the profile in this case is that instead of operating overnight, the whole curve squeezes into just a few hours, and we scale that capacity to 1,000%. We can scale actually as much as we want in that regard. Instead of just spreading over a few hours, we can calculate it in less time. And then we can scale down when we don't need that capacity. Then during the day, during the online part of the day, although in this case you can see it quite flat, the reality is that there might be what we call black swan events, or events that are not very frequent, but still what we learn over time is that they are frequent enough to basically create these profiles of volatility that we've seen over time, where you need for those days to, during the online time, be able to calculate basically all your profiles according to the new events that just came into the markets, right? So it's very important. That's for our customers, it's very important to have that sense of agility, of being able to scale up during the overnight, but also through the events when this happens, when the market event happens. When we check how risk and analytics infrastructure is run on AWS, we got this kind of system. On the right-hand side, we can see the corporate data center with the risk analytic pipeline, still working on it. We got some customers that move those risk analytic pipelines, so part of them also to AWS. At the top of the stack, you can see this pricing and risk services in some of the cases using our partners like Murex. Then below, what you can see is our grid orchestrators, or a grid orchestrator that will run for the duration of the overnight batch, for example. Then the resources that we use for compute that are running into these auto-scaling groups to scale dynamically according to how much capacity you need. And finally, a set of fully managed services that we offer for example, share file storage or in-memory data cache that are able to scale at a very high level concurrent access and still keeping up low latency for the access. So let's explore a bit how to tune those systems. Let's start first with the optimization that we can do with purchasing options. For these systems, we can actually reuse the 3 or 4 different purchasing options that are available. The on-demand for variable and longer running workloads that are in our pipeline. Then for those components where we know that we're going to have a commitment and a steady usage, we can use saving plans and reserve instances and get a discount on the back of on-demand, a significant discount on the back of on-demand for that commitment that we have for those particular instances. And finally, for this type of workloads, spot instances are kind of a differentiator. Spot instances are spare capacity that we got on AWS data centers, and we offer them with a saving of up to 90%. When on-demand users need to get that capacity back, we issue a signal for termination, a notification for termination on those particular instances. But the good thing about these workloads is, in particular, the high performance compute workloads in finance, right, is that they're embarrassingly parallel. They are flexible and fault tolerant. And using auto-scaling groups, Spot Fleet or EC2 Fleet, we can basically build up constructs that when you get a notification for termination in a specific instance, will retry and get capacity from other different type of instance. So for example, you may get a notification for termination on a computer specialized instance, but we may bring instead a memory specialized instance, which yes, is going to give you a different profile, a bit more memory, but for you, it shouldn't matter. It's just giving you a bit more memory. This concept of compute slots in grid workloads make it for it very easy to adopt Spot best practices. For as long as you are flexible, fault tolerant, and heavily diversify on the type of instances that your system can use, you can tap on a very large number of capacity and get all the benefits of the discount that you get on top of EC2 Spot. There's a good integration of these Spot instances with orchestration like IBM Spectrum Symphony and Host Factory, in particular 7.3, and also TIBCO Grid Server, but also with HT Condor and Slurm and so on. We've gone very far to make the use of Spot instances as adequate for this workload as possible, including, for example, releasing last year, in August last year, this capacity optimized allocation strategy. Capacity optimized allocation strategy is, well, as a strategy pattern says, right, some code that we run internally when we need to provision capacity for your auto-scaling group. In this slide, what you can see is in the green blocks, different availability zone with a diversified selection of instances that apply or qualify for your workload, the R5 large, M4 large, and M5 large in each of the availability zones. The bars that you can see are the capacity, internal capacity that we got for those instances. This is an internal metric that we use to feed into capacity optimized to select the instances that will decrease the chances of interruption when we provision new capacity for your grid. So by that, what we can ensure is that we are provisioning your capacity at scale while still reducing the chances of interaction or reducing the frequency of interruption. When we take into consideration our best practices, what we got is that there's many different sources of saving when moving the workload onto AWS. The first one typically comes from doing a lift and shift of the workload and only starting and stopping the instances when you need it during the overnight batch. Typically, that can bring you along the same price that on-premise or even lower. But then you start optimizing even more using the Spot instances or the Spot pricing just to reduce that cost. And then for those type of instances where you may need specific access to CPUs or GPUs, if you got a specific model that can be optimized using those, then also using elasticity and right sizing, just basically dynamically molding how much capacity in an agile way you need to get on and then decommission when you don't need it. And that way you end up basically in a true AWS optimized cost by using that elasticity, selecting the right instances, and adopting the right pricing strategy. And before we close this section, we've been talking about compute, but these other fully managed services that allow you to access concurrent systems to get your data are also quite important. Let's start with in-memory data caches. We got Amazon Elastic Cache for Redis as one of the in-memory data cache that can be used actually to contribute into these systems. Amazon Elastic Cache for Redis is a fully managed Redis compatible in-memory data store. It can scale up to 170 terabytes of in-memory capacity. And if you check how much capacity, how much concurrency can you get from the R5 24X large, you can nearly get up to 400K requests per second, and this is just one of the instances that you can add on top of it. You can support for more shards and replicas into the system and get these high levels of concurrency that you need while still preserving that very low latency. In some cases, our quantitative analytic libraries may still have dependencies on a POSIX file system, but our system has the need to scale up. In those cases, we can make use of a fully managed high-performance share file system like Amazon FSx for Lustre. Actually, it's even better. FSx for Lustre can only be started for the periods that you need as a distributed file system, in this case for the overnight batch. And during the time that is not started, you can keep that data into S3. So effectively, before the batch start, you start a new Amazon FSx for Lustre, which is a massively scalable parallel file system. You dimension it based on what is the number of partitions and therefore the throughput that you need and the total capacity that you need out of it. And it starts reacting as a cache for the S3 capacity that you got in place. When you switch off the Amazon FSx for Lustre, all that data is preserved into S3 as you are using it as scratch mode. And while you're using it, you still get all the concurrency access level that you need. And with all those systems, what we got is quite a lot of customers making use of these best practices to adapt their systems onto AWS. I would like to introduce Daniel Kazarinow for him to basically tell you how the journey was at Standard Charter to use all these techniques and services.
Thank you, Carlos. Hello, everyone. My name is Daniel Kazarinow. I have started my professional career in London as a summer intern in 2006 and worked as a support analyst for 2 years at Merrill Lynch. After that, I have joined HPC team in Barclays Capital, where I was responsible for the technical design and delivery of 2 largest grids in the bank, equity derivatives and fixed income exotics. In 2019, I have decided to accept the challenge of bringing the grid at a Standard Chartered bank to the next level, and I have moved to the sunny Singapore. Grid was the first workload on the AWS cloud in the bank, and my responsibility naturally expanded to cloud operations function as well. This year, my focus is on evolving cloud SRE and making sure our cloud and grid platforms are stable. We are a bank, so what do we really do? We are growing, moving, and lending money in layman terms. We are present in over 60 countries, and last year we have celebrated 160 years anniversary in Singapore. We are printing banknotes in Hong Kong since 1862. And we are a proud sponsor of Liverpool FC Premiership champion this year, and also support marathons across Asia, Africa, and now even in Europe. Like many organizations, we have our valued behavior, helping to maintain the focus on the goal. Do the right thing with clients being in the center. Embrace the change, be the change. Never settle. Standards and simplification is our recipe for success. Managing thousands of servers as one, that's the key. Better together. As the famous quote says, if you want to be fast, go alone. But if you want to go far, go together. Let me walk you through our cloud journey. In 2013, we were running out of the capacity in our data centers. And we had a couple of options, either invest in a co-location or go to cloud. Towards the end of 2013, we have started working on a grid POC. We have completed compliance sign-offs. We have set up the connectivity, VPN-based connectivity. It took us approximately 2 months. And then we built the grid within the cloud in 2 weeks' time. As you can imagine, we had a positive outcome and decided to work on the enterprise level development grid. So in 2014, we have set up the direct connect lease lines, secured the environment, and integrated programmatic engine procurement. Development grid went live. After that, we were working hard to deliver our production setup. So again, we went for the similar activities like a new segregated network setup, even more compliance and regulatory approvals, and making sure that everything works spot on once we go live in a production. In Q3 2015, we are live. Next year, we have already reached the grid scheduler's 7,000 licensing cap, and we were unable to expand the grid further. Hence, we have moved to the open source and in-house written schedulers. In 2017, we have deployed the first application via internal CI/CD pipeline, and our grid was already reaching 20,000 vCPUs. In 2018, we have went live with the security monitoring and auto-remediation Lambda-based SecMon. That was before even the AWS config was available. We also went live with our first production application, which kept customers' data. At that point of time, we were already utilizing 100 million EC2 hours per month. In 2019, we had 160 active accounts. We were using approximately 200,000 concurrent vCPUs, and our grid cost per vCPU went from 9.6 cents to 2 cents per hour. What's happening now? We have openly declared our cloud-first strategy. We have over 400 active AWS accounts, and this number is rapidly growing. We are utilizing approximately 2.5 million of EC2 hours, and we have managed to drop our grid engine cost even further to 1.5 cents per vCPU hour. This slide shows last 2 years of the cloud compute demand and the method of capacity purchase. As you can see, we have significant uptick into 2020, where we openly declared our mentioned earlier cloud-first strategy. We run way more for far less. We have purchased saving plans and applied other cost-saving techniques. This is the orange portion on the graph. The grid transition to EC2 Spot started at the end of 2017. That's the green bit, spiky bit on the graph. We have reached nearly 6,000 concurrent EC2s in August this year. In 2017, we have started using CI/CD for infrastructure as a code cloud deployments through our rich ecosystem of tools integrated with the pipeline. Different application maturity, level, and usage of the VX toolchain. Cost optimization. This is something close to my heart. Because do you really know the cost of your in-house infrastructure? It's very, very difficult to be accurate in that discipline. With the cloud, you can see the result of actions pretty much next day, encouraging even more experiments. You do the change today, and next day or 2 days after, you baselining and see the impact of your change. So we were really excited to start experimenting quite heavily in 2017. We have moved our engines from the R3 to R4 EC2 family. So we pretty much done the hardware refresh overnight. To put it into a perspective, similar on-premises activity took us nearly 1 year. Not only we have saved 1 million of our running rate per year, but also we have achieved 20% performance improvement because we started using newer, faster Broadwell chipsets with AVX2 instructions. After that, we have replaced grid provisioner from the VCAC to in-house written microservice utility based on Lambda, and where we kept the state on the RDS in the RDS database. We have achieved much faster grid scale up and most important scale down. Before, with the previous tool, the termination of 150 instances only took us 60 minutes. With the new utility, we have managed to bring it down to 3 minutes. In Q3 2017, we have switched off hyperthreading on grid EC2 engines and moved from R4 extra large to M4 16 extra large. XVA batch wall clock time decreased from 13 to 10 hours, and average task runtime reduced from 200 to 150 seconds. The cost of the XVA batch has been reduced by approximately 10%. Memory ratio went up by 5% as well. And we have managed to increase the development capacity by 100% because we have shifted the licenses from production to the development. At the end of the 2017, we have started development experiments with the Spot for grid. We had great results and per second billing. And in 2018, we have started moving production grid of expensive on-demand to Spot instances. Just because of this activity, we have saved 2 million per first year. 2019, we have already highly diversified pool of Spot instances in prod. We have managed to break the cheap, fast, better relationship stereotype. Cost of the entire grid went down from over 9 cents to 2 cents per vCPU hour. Now, with savings plans allowing us to run more for less, and the Spot, which have saved us 9 million within the last 1 year. And as I have mentioned, we have reduced the cost of the grid engines to 1.5 cents per vCPU hour. So elasticity. You can see from the left, January 2017, January 2019 in the middle, and on the right, July 2020. At the beginning of the 2017, we were not using Spot, and the usage was still fairly low. The middle graph, January 2019, shows baseline at 600 instances and much higher peaks in correlation with moving to Spot as yellow spikes on the graph. Given the business growth with the optimization configurations we have done, we have managed to keep our cost neutral between 2017 and 2019. July 2020, on the right, with Cloud First, has resulted in steep acceleration of cloud adoption, hitting in August mark of 6,000 concurrent VMs. What are our next steps? We continue with lift and shift for legacy development workloads, automate processes and a cloud management platform, accelerating velocity of the cloud migrations, and allowing to move to production even more applications. We continue with never-ending cost optimization. We enhance the grid provisioner by using additional AWS regions, increase resilience, automatically terminal idle engines, and attach EBS volumes with preloaded QA libraries. We heavily invest in the trainings, so bank supports through the virtual classes and self-paced online training. We were running along with the AWS immersion days, and we are planning to resume those sessions after the pandemic is over. We'll run more game days and constantly increase our bar for security controls. To summarize, as you can recall, one of our values stands for better together. We wouldn't be able to get where we are at the moment without the AWS team, our cloud enablement team, cloud governance, risk and control, security and networks colleagues. We have opted in for enterprise support, hence we are looked after well by the AWS business development, technical account manager, and solution architects. On our side, however, strong collaboration with quants, developers, security, networks, legal, and compliance, and cloud teams took us where we are now. On that note, I would like to thank you for your attention, and I will hand it over back to Carlos to wrap up the session. Thank you very much.
Well, thanks for that, Daniel. I love hearing stories like the one from Daniel, right? Where you start with that cost optimization and so on, but at the center of it, you also have all the performance improvement that they've done and the agility that they have to innovate for their business. I would like to close these sessions with mentioning our partners as well. These projects are complex, and in some of the cases, our customers are making very good use of our grid consulting partners like DXC, Contino, CloudReach, Accenture, GFT, Capgemini, First Derivatives, using the platforms from Murex, FIS, and we have, for example, in our marketplace, AWS Marketplace, a typical grid server offering, and a very good integration with Spectrum, Symphony from IBM as well. Same applies. This is not all about compute. AWS is the right place to have your grid workloads. This simplifies also the way that you can get access to your usual data for risk analytics, for example, by using very secure connections with private link and getting access from Bloomberg, or our services extended like data exchange, where you can get data from Reuters, Verisk, from public APIs, their connections for exposing endpoints with Refinitiv and so on. So all of this makes of AWS the right place to migrate your grid workloads. And with that, I'd like to close. Thanks a lot to Daniel for showcasing all the grid journey from Standard Chartered, and we can start with questions and answers. Thank you for your time.